Okay, in this very short video, we are going to just define the ideas of velocity and acceleration with respect to the vector function that we've talked about before. With this, we're going to finish section 13. So this is just the beginning of section 13, or sorry, chapter 13. This is just the beginning of section 13.4. If you open section 13.4, you will see that there are many more ideas covered there, but we're just, because the semester is the way it is with everything happening with the disease, we're just going to define the velocity, the idea of velocity, the idea of the acceleration. Many of the ideas covered in this section, you have already covered them in mechanics and physics. So we're just going to stick to the basics, okay? So let's say that a particle moves along a curve defined by r of t, okay? Well then, how do we define the velocity? The velocity is a vector defined as the derivative of the position function of the vector. So that's velocity, okay? Which is the rate of change of the position vector, and the acceleration is the derivative of the velocity, which by this idea is just going to be the second derivative of the position function, okay? Make sure that you understand that you remember the difference between velocity and speed. Velocity is a vector, so it has a magnitude and direction, whether the speed just it's a scalar, which is the absolute value of the velocity. Okay, so let's do a very simple example. Given the position function of a particle find the velocity, acceleration, and speed of the particle at t is equal to 2. Okay, so the position function is given by t squared 2t ln of t. Okay, so what did we say? The velocity is equal to the derivative of the function, and the derivative of the vector function is the derivative of each of the components. So derivative of t squared is 2t, derivative of 2t is just 2, and derivative of ln of t is 1 over t. Okay, now finding how much is the velocity when t is equal to 2, that means just we plug 2 everywhere for t, and you get 4, 2 and 1/2. Okay, so now if I want to find the speed here, I just have to find the magnitude of this. So the magnitude of the velocity, so this vector has a velocity 4 squared plus 2 squared plus 1/2 squared, which is square root of 16 plus 4 plus 1/4. Okay, and that's equal to square root of 20 plus 1/4 is equal to square root of 85 over 4, which is equal to square root of 85 over 2. Okay, and then the acceleration vector is equal to the derivative of the velocity. The velocity is given by this vector right here, so the derivative is going to be derivative of 2t is 2, derivative of constant is 0, and derivative of t to power negative 1 is negative 1 over t squared. Okay? Sorry, I made a mistake here. So 4 times 20 is 80. 80 plus 1 is 81. My bad, sorry. So square root of 81, that's 9 over 2. Sorry about that. So 4 times 20 is 80. 80 plus 1 is 81, not 85 as I had previously. Okay? And then we talked about integrals of vector functions, so we're going to use them if we have to solve this question. If the acceleration vector of a particle is given by this vector, if the acceleration vector is given by 1 to 6t, okay, find the position function where these following initial conditions are given. V of 0 is equal to j minus k, and the initial position is, that means the position function at the beginning is I minus 2j plus 3k, okay? So we have the acceleration vector 1 to 6t, okay, what is given. We have the velocity vector evaluated at 0 is, right, so I don't have the unit standard vector I in this expression, that means it's 0, right, 1, negative 1, okay, and the position function evaluated at 0 is the vector 1, negative 2, 3. Okay, the question is how much is the velocity vector and how much is the position vector, okay? So knowing that the acceleration is equal to derivative of the velocity, that implies that the velocity is equal to the integral of the acceleration. Okay, so that's what we do. Improper integral of this vector right here, so 1 to 6t dt, and we said that the integral of a vector function is just the integrals of the components of these vector functions, so that is, we get the integral of 1 is t, the integral of 2 is 2t, and the integral of 6t is 6t squared over 2. Now here, be careful. I have a indefinite integral, and an indefinite integral, when we evaluate it, we have to add this constant c, if you remember from Cal 1 and Cal 2. But in this particular case, c is also going to be a vector, okay, because these are vector functions. So that means that v of t is equal to t 2t 3t squared plus c. Now how are we going to find c? Well, we're going to look at the initial condition. So that means v of 0 is equal to, how do I evaluate v of 0? If t is 0, I substitute here 0 everywhere, so that's 0, 0, 2 times 0 is 0, 3, 0 squared is just 0, plus c is equal to this vector that's given here, 0, 1, negative 1. Okay, that means that this vector here is 0, 1, negative 1, and now you just go back to your expression for the velocity vector. V of t is equal to t, 2t, 3t squared plus 0, 1, negative 1, and this is just a very simple addition of factors. T plus 0 is t, 2t plus 1, and 3t squared minus 1. Okay, by the same logic, if v prime is equal to, if v is equal to r prime, then r is equal to the integral of v dt. So that's the integral of t, 2t plus 1, 3t squared minus 1 dt, which is equal to t squared over 2. Integral of t is 2t over 2, so 2 and 2 cancels out, so t squared plus t. Similarly here, t cubed minus t. And again, it's an indefinite integral plus another vector c1. Okay, and now how are we going to find c1? Well, we'll look at the initial position of the particle. So r of 0 is equal to, here plug 0 everywhere, and then you get the 0 vector again, plus this vector c1 by this condition is equal to 1, negative 2, 3. So the vector c1 is equal to 1, negative 2, 3. Now add these two vectors and you find r of t. That's t squared over 2 plus 1, t squared plus t minus 2, and the last one, t cubed minus t plus